Hi, we are students from CS1231 Group 7 project, and today we're going to talk about Chinese Remainder Theorem, of course CRT. I'm Li Leong. I'm going to introduce you why CRT, where does this CRT come from in history. Yuana will explain about basic knowledge about CRT, the concept of CRT. Junyang will talk about the how does this CRT works by using example. Ruquan will talk about how does this CRT come from by using logics and proofs. Well, lastly, James will talk about how does this CRT applies in our real life. Before we go into the point, I'm sure all of you will ask, okay, what is CRT? And where does this CRT come from? Basically, CRT is come from a book which is called The Mathematical Classic by Sun Tzu. You all know that Sun Tzu is one of the famous mathematicians during the 3rd century. He actually come out with this question. There's a series of unknown numbers such that if it's divided by 3 gives a remainder of 2, if divided by 5 gives a remainder of 3, and if divided by 7 it gives a remainder of 2. So what's this number? A lot of people will go and guess, okay, maybe 5 is divided by 3 leaves 2, 5 divided by 5 leaves 3, or 7 divided by 2. But the question is really, it's kind of troublesome to guess a number which have to satisfy these 3 conditions. So this question has been circled around for about 9 centuries until in 1247, there's this Chinese mathematician called Qin Jiu Shao. He actually just gives this solution from a book which called Mathematical Treatise in 9 sections. In Chinese we call it Su Su Jiu Zhang. They actually come out with this algorithm called Euclidean algorithm, such that we find the greatest common divisor. Okay, for those who actually don't know what is common divisor, I give you an example. So let's say 10, 12. The greatest common divisor is 2, because since they actually can be divided by 2, and the maximum number that can be divided is 2. So this is called about Euclidean algorithm. So what is CRT? CRT is basically to calculate the congruence in number theory. Okay, question again, what is congruence? So I'll pass this definition of congruence to Joanna, and he will be explain the concepts of CRT. Then you want to know what is congruence.
The theorem statement of the Chinese remainder theorem is as follows. Suppose we have positive integers ranging from n1 to nk. All of these integers are pairwise coprime, which means that if every pair of distinct integers in a set share only one common divisor, that is the integer 1. Then, for any given sequence of integers ranging from a1 to ak, there exists an integer x solving the below system of simultaneous concurrences. Just to note, we are dealing with sequence of values ranging from a1 to ak and not a set. Hence, the equality of 2 integers in the sequence is allowed. The simultaneous concurrences are shown below. Furthermore, all solutions x of these systems are concurrent model of the product of all the n's. Let's call it capital N. That is because x is concurrent to y model ni for all values of I ranging from 1 to k, if and only if x is also concurrent to y model capital N. As an addition, sometimes we can solve the simultaneous concurrences even if the ni's are not pairwise coprime. In that case, the solution x exists if and only if ai is concurrent to aj, model of the greatest common divisor of the ni and nj for all I and j. All solutions x are the concurrent modular with the least common multiple of the ni.
In order to prove the Chinese remainder theorem, let's consider the Bezout identity, which states that there exists integer x and y such that ax plus by equals to b. Where a and b are any integers, d is the greatest common divisor of a and b. There is also an algorithm called Euclidean algorithm, which help us to find x and y quite fast. For example, let A equals to 5 and B equals to 378. Then D equals to 1 because 5 and 378 are co-prime. By Bezout identity, there exists x and y such that 5x plus 378y equals to 1. We now try to find x and y. The original equation is equivalent to the following. Now, let z equals to x plus 75y. We can then simplify the equation into. Let's call another variable t which equals to y plus z. We can then transform the equation this way. Now we can tell that t equals to 1 and z plus t equals to 0. Hence, z equals to minus 1, y is then equals to 2. Call the following. We can then find x, giving us x is equals to minus 151 and y is equals to 2. On. Now let's try to prove Chinese remedial theorem. First, we denote Ni as follows. And since M1, M2 up to Mt are mutually co-prime, therefore Mi and Ni are co-prime for all I. Let's take a look at the following example. We found N1 to be 378, N2 to be 70, N3 to be 135. To find N1, simply take the big M, which is the multiplications of all the modular number 5, 27 and 14, and then dividing it by each equation's modular number as above. Then repeat to find N2 and N3. X can be seen M1 and N1, which are 5 and 378 respectively, are co-prime. So are M2 and N2, M3 and N3. Now let's come back to the proof. Apply Bezout identity for Mi and Ni, which are co-prime. There exists integers Ri and Si that satisfy the following equation. Let Ei equals to Si times Ni, then it's obvious that Ei is equals to 1 mod Mi, and Ei equals to 0 mod Mj for all j not equals to I. Consider Bi times Ei. Bi times Ei is congruent to Bi times 1 mod Mi and is congruent to Bi mod Mi, and Bi times Ei is congruent to 0 mod Mj for all j different from I, because Ei is congruent to 0 mod Mj. We then construct x0 as follows. Therefore, x0 is the solution to the systems of equations, because the way we construct x0, which equals the sum of Bi times Ei. For each Mi, x0 is congruent to Bi mod Mi. For example, let's clear the picture by trying to find x0 for the previous example systems of equations. When M1 is equals to 5 and N1 is equals to 378, we can find R1 is equals to minus 151 and S1 is equals to 2, as discussed before in Bezout identity. Next, apply Euclidean algorithm similarly for M2 is equals to 27, N2 is equals to 70, and M3 is equals to 14, N3 is equals to 135. We can then obtain R2, S2, R3, and S3 pretty quickly. We will try to construct a solution X0. Sub each Bi, Si, and Ni in. We can then get X0 is equals to minus 1156 this way. We can now test to see if X0 really is the solution. We can see that X0, which is equals to negative 1156, satisfies each of the congruent equation because negative 1156 minus 4 is equals to negative 1160, which is divisible by 5 in the first case, and it is proven true for the next two equations as well. Therefore, X0 is the solution to the example system of congruent equations. Now let us move to the last part of the proof. Suppose X1 is another solution to the system. Then X1 and X0 will both be congruent to Bi mod Mi. X1 minus X0 will then be divisible by each Mi. And since M1, M2 up to Mt are pairwise coprime, X1 minus X0 divisible by each of them will mean X1 minus X0 is divisible by their product, which is M. Therefore, any two solutions actually differs by a multiple of M.
These are some of the applications of the Chinese remaining theorem. Normal RSA algorithm calculations are done in the form of mod n, where n is the product of two large prime numbers p and q. N equals to p times q, where p and q are large prime numbers. Calculations done in this manner are usually very huge, and n usually goes up to a 4096-bit integer. So wanting to find what number divides n in the form of z over nz can be very time consuming and tedious. However, there's a faster heuristic to solve this problem. The Chinese remainder theorem does calculation in the isomorphic ring of p and q instead of that of n. Therefore, p and q are normally about the same size because n is so big. This size is about the square root of n, and calculations in this representation are much faster. However, note that RSA algorithm implementation using this isomorphism are more susceptible to fault injection attacks. Another application that is used in the Chinese remainder theorem is known as secret sharing, where what you do is where you take a set of shares and distribute them among a group of people who, all of them, but no one alone, can recover a secret from the given set of shares. Each of the shares is represented in a congruence, and the solution of the system of congruences using the Chinese remainder theorem to decode the secret is to allows the secret to be recovered as a whole. Therefore, the Chinese remainder theorem can be used to conceal and decrypt messages. These are just some of the applications of the Chinese remainder theorem.
I'm sure you already know what is CRT about, so let's quickly go through a summary of CRT. CRT is basically a theorem to calculate a series of numbers such that if, let's say, it's divided by some values, it gives a remainder of some values. This theorem actually applies to some encryption applications like secret sharing, as what James mentioned just now. So if you all want to know more details about Chinese remainder theorem, go to our website for more details. And thanks for watching.